Here we're going to look at how to transpose graphs to go from a u of x graph as we're given here. So we're given u of x, so you might want to get this in explicitly, right? Get u of x in there on the y-axis, and x is on the x-axis. So if you were given this u of x graph, how do we make sense of it? And then how do we generate the f of x graph? And now, since we have our calculus understanding of that f of x is negative du dx, we'll utilize that. But first, let's just go back and remind ourselves of how we understand the u of x graph. So here, if you were given this graph to look at, and let's say you're not given the mathematical expression to be able to actually take the derivative, but we want to get some understanding of what this potential energy function is showing us. Well, the first thing it's showing us, as I have here in purple, is when there is no force acting on the object, right? So if force equals negative the slope of the tangents, right, negative du dx, then where you would have a tangent line, right, with no slope, you are going to get no force. Where you have no force, the object is said to be in equilibrium, and there are definitely three types of equilibrium that you need to know, and you need to know the language that goes along with them. The first is neutral equilibrium, and that's when the object would be sitting in these plateau regions. By object, I'm now talking about our marble. So we're going to look at how the marble rolls. And what we want to think about is if we were to displace the marble a little bit to the right or a little bit to the left, would it be inclined to go one way or the other? And the answer is no, hence neutral. It's a neutral situation. Well, how about for stable equilibrium? Stable equilibrium is, again, language that we need to know: neutral, stable, unstable. Stable equilibrium, I think, is just as the name implies, that when that marble is sitting in a trough, if we were to displace it a little bit to the right or a little bit to the left, it would be stable. It would want to return to this position. And then, hopefully, unstable makes perfect sense, because if that marble were, again, displaced a little bit to the left or a little bit to the right, it is not stable. It would not want to return to this position. It would want to run away from that position. So, as far as our marble analogy goes, I'm not going to go through that with you in detail here. If we did flick this, let me clean this up a little bit now. If we did flick this marble to the right, we gave it a little bit of kinetic energy in this direction, it would, of course, continue to roll. It would speed up, maximum speed, slow down, but not stop, because we haven't reached back to our initial energy position, go over the plateau, and would keep going to the right. This would be unbounded. So I think that understanding is clear to us at this point. But how about if we weren't given this f of x graph, and we're being asked to generate the f of x versus x graph? Well, what you want to do is make it all about slope of the tangents, right? So f of x equals negative du dx is all about slopes of the tangents, and I would go along and just quickly put little tangents in there all over the place, right? They don't have to be even perfect, but just get them in there and try to think about how the slopes of the tangents are changing in this problem as you go along, and then the f of x graph is going to represent the magnitude of the force will be the steepness of the slope. So my equilibrium points are nice because I automatically get the f equals zeros in there, right? So these are all my neutral, stable equilibrium, unstable equilibrium, stable, and neutral again. And then the only thing that I think is a little tricky is that darn negative, because here my slope is positive and it's small at first, so small values at first, and then getting bigger, bigger, bigger until I have an inflection point somewhere in here, right? maximum force, and then of course it's still going to be positive slope, but that negative out, or I'm sorry, a negative slope, but that positive, the negative out in front makes it a positive slope. So still positive, but getting smaller and smaller and smaller back to 0. So you can generate this function qualitatively, but you really have to keep that negative in mind and make sure you're handling it appropriately. And then as it shows here, please get this into your notes, that let's say you were given this f of x graph and you were asked to generate the u graph. You will be taking delta u, the change in potential energy, is negative the areas, and I use my little slices here, my kind of trapezoid rule from calculus to estimate areas. Small area, right? Small change in potential energy. Bigger changes in potential energy. These are positive areas, but the negative in front means that the potential energy was decreasing, as it shows here. And of course, you must be given U initial. So delta x equals negative the area, and actually we should add in here must, right? So try to sneak this in somewhere. Must be given U initial. So get that in there as well. So hopefully this makes sense based on what we've talked about. We're going to do some homework practicing some of this as well. And that concludes what I think we need to really understand about energy. So there's a lot in this chapter, and hopefully it's been good.